In this video, we're going to look at rules of inference. So what we're heading toward is validating arguments and using proofs to help us with programming, writing programs. So we'll start with this idea of valid arguments and kind of look at how there are different rules that we can follow to help us determine the logical consequences of an argument. Okay, so the first example we've kind of seen like this is the Socrates example, which is all men are mortal. Socrates is a man, so we can conclude that Socrates is mortal. Okay, so we call, I just realized that they referred to a line that's definitely not there. This is supposedly the line. Okay, so these are called the premises. That's what this statement says right here. The premises are above the line. The conclusion is below the line. And then what we have is an argument that could be written in this form using our quantifiers. So for all x, where x is a man, that implies that x is mortal. Then we're told specifically that Socrates is a man, and therefore from the above, Socrates is mortal. Okay, so this particular rule of inference is called modus ponens. Okay, the basic structure of the modus ponens argument looks like this. P implies Q, and then we say P happens. So these are our premises, and then we can conclude that Q will happen. I just realized I kind of drew that a little bit low, but that's all right. I'll do the tautology a little bit lower too. So that's the basic structure of this argument. By the way, I do want to note it's the same thing if P goes first and then we say P implies Q, and then we still would conclude that Q is going to happen because we're told that P is happening. That's what this says. P is happening and P implies Q. Okay, that if P happens, then Q happens. So that basic structure is what we're following for the argument. Written as a tautology, so this is like when we're doing the truth tables, the tautology equivalent would look like this. P and P implies Q. So those are the two premises. This, if those two premises happen, notice we're using and, so they both have to happen, that's going to give us Q. That's how we'd write that for a truth table or as a tautology. Okay, so let's write it in words. If P happens to be it is snowing and Q happens to be I will study discrete math. So the form of this argument with these examples would be if it is snowing. Wow, snowing starts with an S. If it is snowing, then I will study discrete math. So that's the first premise. The second premise is it's snowing. And so we would conclude, therefore, I will study discrete math. So that's how that would look written out with those particular values for P and Q following the modus ponens argument. Okay. Okay, so let's look at the next one, modus tollens. So modus tollens is actually similar. It starts with the same P implies Q, but this time, this time we say, oh, it doesn't want to let me erase, there we go, not Q. So Q doesn't happen. That means that P didn't happen. That's how modus tollens work. So if we use the statement, if P happens, then Q happens, but I tell you Q didn't happen, you can conclude then that P didn't happen, okay? In tautology form, that means we would be pairing, not, oops, sorry, I bumped the board while I was doing that, not Q and P implies Q. Then that leads us to not P. Okay, so let's write this with the examples of P being it's snowing, Q being it's I will study discrete math. So we'd start with the same first statement. If it is snowing, I keep missing the S. The is throwing my brain off. If it is snowing, then I'm going to abbreviate that. Study discrete math, just so I could fit it all on one line. And then I told you, I'll say I didn't study discrete math, which means you could conclude it didn't snow. Now, that doesn't mean that if it doesn't snow, I won't study. It just means that when it's snowing, I'm going to go study because I have nothing else I can do. All right. Okay, let's look at a hypothetical syllogism. Hypothetical syllogism. Okay, so this one uses two if-then statements. It's their premises. So P implies Q. Q implies R. So we can conclude that P implies R. So it's saying that we're building on two arguments that kind of piggyback together. As a tautology, we would be saying P implies Q happens and Q implies R happens. And when those two happen, P implies R. All right, so here we go. This time we're going to need three values, P, Q, and R. So P is it's snowing, Q is I will study discrete math, R will be I will get an A. Okay, so first thing we say, if it is snowing, consistently see me make the mistake. If it is snowing, then I will study discrete math. If I study discrete math, then I will get an A. Therefore, if it is snowing, oh my goodness, I did it. If it is snowing, then I will get an A. Because the snow is guaranteeing that I'm going to stick around and do studying, and that's going to help me get an A. So I'm concluding that having the snow happen is going to actually help me earn an A. All right. Oops, sorry, bumped the board there. Disjunctive syllogism. Disjunctive syllogism. Okay, so for this one, we're going to have an or statement. So P or Q. And I tell you, not P. So we would conclude then that Q happens. So it's the idea that we have this or statement, and then I'm going to tell you that one of them is not going to happen. So since it's an or statement, that implies the other is going to happen. Okay. The tautology for this one, P or Q and not P, that's going to imply Q. All right, I gave myself space here because there wasn't much at the end of that page. So the examples here. Okay, I will study math, and then different Q this time, I will study English literature. Okay, so the first argument is I will study discrete math or I will study English literature. Okay. Then I'm going to say not the first one. So I won't or will not study discrete math. Maybe because I'm already getting an A or something like that. Therefore, I will study English. English literature. Awesome. There we go. Okay. The next one is actually an interesting one. and you'll see why it's kind of interesting. So here's how it works. We actually only have one premise. We start with P. And that's our one premise. And to that premise, then, we can add anything we want with an or statement. So what I'm saying is that if I have a premise happen, then it's possible to add anything I want to that. And with an or statement, because the or statement allows me to kind of have a choice. So here's the tautology for that. It says that P implies P or Q. So here we go. Here's an example. P is going to be, I will study discrete math. Q is going to be, I will visit Las Vegas. Very different, right? Really doesn't like connect to each other. So here's the idea. I'm going to say, I will study discrete math. That's the premise. So I can conclude then, and it remained truthful. Therefore, I will study discrete math, or I will visit Las Vegas. And that holds truth because of the or statement. So because I did the first one, I can pair it with anything, or I will go to the moon, or I will spontaneously turn into a robot. Okay, so the idea is that the or statement allows me to add anything else to it I'd like in my conclusion because the one premise is true. So it doesn't really matter if the second one is true or not. Maybe it will happen, maybe, but that's the idea. Okay, now simplification kind of goes the other direction and it uses an and statement instead. So we're given two things, P and Q happen. Therefore, P is going to happen. Well, duh, I was told P and Q. Okay, so that one is kind of a way of simplifying an and statement. So as a tautology, we start with P and Q, and that's going to give me P. I could have concluded, by the way, Q. It would have worked the same way. Because they're both and, right? It really doesn't matter which one I pick. Okay. Because they both happen with the and statement, you can go ahead and conclude the other one as well. It really doesn't matter. Okay. So let P be, I will study discrete math. Let Q be, I will study English literature. Okay. So my premise is I will study discrete math and English literature. So I'm going to cheat there and use the English language to not write the full sentence. So I will study discrete math and English literature. Therefore, I will study discrete math. I've definitely accomplished that task. Because I said both of them were going to happen. Kind of like a big duh. All right. Okay. Conjunction. So conjunction pairs two things together, two premises together. So I say P happens, Q happens, therefore P and Q. They both happened. So this would be P happens and Q happens. Therefore, P and Q. Now, the book does do like a little distinction where it's like P all by itself, Q all by itself. Like they put parentheses around just so you know that they're both individual. And then P and Q happen. A little funny looking. I will study discrete math. So that's my statement. And then I say, I will study English literature. Wow, that's not how you spell literature. So there's my two premises. Therefore, I can put them into an and statement. I will study discrete math and English literature. All right. And one more, resolution. So resolution looks like this. Resolution says we start with the argument with two or statements, not P or R. P or Q. So we can conclude that Q and R are going to happen. Okay, so we're saying P doesn't happen or R happens. We say P happens or Q happens. So what's going to happen is because those two first statements end up being kind of contradictory, we end up with the latter two happening. So here's how the tautology looks, not P or R, and P or Q. So that gives us Q and, I'm sorry, or. Oh, I just realized, I'm so sorry. I put an and that should have been an or. I'm so sorry. That Q is going to happen or R is going to happen. I'm so sorry. Wow. Q or R is going to happen because they are based on P. One with P not happening, the other one with P happening. So one of those two outcomes are going to happen. Wow, sorry, I definitely wrote that wrong and said that wrong. I was actually fighting it in my head and didn't listen to my voice. All right, that's all right. So here, let's write it as an example. Okay, so let PI will study discrete math. Okay, so first statement is, I will not study discrete math, or I will study English. I should probably make this a little bit smaller. I'm not going to fit them all. I'm going to go ahead and put the next sentence on the same line just because of space. The next premise would be, I will study discrete math. Discrete math, or I'll study databases. So the conclusion is, therefore, I will study English or databases. Sorry, I ran out of room, so I skipped writing the word literature. All right. That's how we could write the conclusion there. All right. So I'm going to show you an example. Okay. And then we will go ahead and we have another set of arguments we have to learn. All right. And then I'm going to do a separate video with several examples, kind of having talked about those single arguments. Okay, so from this proposition, show that Q is the conclusion. Okay, so here's how we kind of do this. They break it up a little bit like how you might have seen in geometry if you took geometry. So the first step is we're going to start with our premise. And the premise is P or Q implies S. Sorry, R. Q implies R. So that's our first thing. And the reason is, that's our premise. They told us that. Okay. So from this, we started with an and statement, and you can go ahead and scroll back up and look for the and statement. But there is only one that uses the and statement, and that is simplification. So from simplification, we can go ahead and conclude either P happens or Q implies R happens. I just realized, I'm so sorry. I just realized there's an error. I'm so sorry. I don't know how that happened. Let me see if I'm looking at a different argument. Wow. Okay. No, I'm not. I'm so sorry. So this is written incorrectly. This should actually be P implies Q. Can you please make that change? I'm sorry about that. It should be P implies Q. So here, let me change this. So either P happens and P implies Q. Okay, so using simplification, I could either assume one of those. Okay, it doesn't matter which one I assume. For right now, I'll just assume the first one. I'm going to assume P happens. Okay, that's using simplification. And I'm using simplification on number one. So I'm going to refer to the step. I could have also concluded, by the way, that P implies Q. So that's what I'm going to do. I'm going to use P implies Q. I'm going to use simplification again on the first step. And what that sets up for me is modus ponens. Since I have P and I have P implies Q, that gives me Q. Oops. So that is modus ponens. And that's on numbers, using numbers 2 and 3 to give me modus ponens. So I'm referring to the two arguments. Technically, remember I wrote that it could happen in reverse order. The list of the premises doesn't matter as long as the two premises are actually there. Okay. Let's look at this example. This time we're actually looking at written out premises. And what we're going to do is we're going to write this into propositional variables and using propositional logic, and then we'll step through the argument. Okay, so here we go. It is not sunny this afternoon and it is colder than yesterday. So let's go ahead and let P be. So I could let P be it is not sunny, but because they're using the word not, I'm tempted to let that be not P, right? Like using the not symbol. So I'm going to let P be it's sunny. This afternoon. Okay. And then Q is going to be, it's colder than yesterday. Okay. Now we have, we will go swimming. So that's going to be R. We will go swimming. And that's going to happen only if it's sunny. Okay, but I already have it's sunny listed as P. Okay. If we don't go swimming, which we already have, then we'll take a canoe trip. Okay, there we go. So PQR. Now this will be S. S will be take a canoe trip. Okay. If we take a canoe trip, then we'll be home by sunset. Okay, last variable, T. Home by sunset. I'll put we will. Be home by sunset. All right. So here we go. Using these labels, I'm going to zoom out just a smidge just so I could do this. I'm going to write these then in premise form. So this first one is going to be not P and Q. We will go swimming only if it's sunny. Okay, so that's saying that when it's sunny, we'll go swimming. So that's actually going to be the form R implies, no, only if it's sunny. We go swimming only if it's, so I think that's going to be, P. Yeah, I'm thinking that's P implies R. I'm referencing something that the publisher gave. This is where I pulled the example from, and they don't have it written like that. So, hey, we'll find out if I'm wrong. They have it written reversed. But I feel like when you're saying it's sunny, then we go swimming, right? Like that to me sounds like the way the premise is supposed to be worded. Okay, we'll look at it in a second. We'll see if that's correct based on the argument. Okay. If we do not go swimming, then we will take a canoe trip. Okay, so not swimming, that's not R. Then we go on a canoe trip, so that's S. All right. If we take a canoe trip, we will be home by sunset, so that's S implies T. Okay, so I'm going to highlight the one that is different from the way they showed it in the example where I pulled this from, but we'll look at it as we go through. Okay, so here we go. We want to basically figure out if these premises are going to lead us to the conclusion. Oops, I thought I was still in the highlighter. To this conclusion, we will be home by sunset. In other words, we're saying that this is supposed to give us T. All right. So we're going to use the inferences and the premises to see if we can push out T as a conclusion. Okay. So here we go. Let's start with the first inference. I might need more space. So I'm sorry to do this. I might have to erase this just for space. You might be able to squeeze it in when I'm writing on this screen. It's, you know, I'm a little bit clunkier. I have to write a little bit bigger. So hopefully you can squeeze it in. I apologize if you can't. Okay, so let's start with the first premise. So this is the step, and then we'll have the reason. All right, so first step, not P or Q, and that's from the premise. Oh, and Q, I'm sorry, not P and Q. Okay, so we have one thing I can use with an and statement, and that is, my brain shut off there. One thing we can use an and statement is we can use simplification. Now the question is, which one do we want to simplify to? Either not P or Q. So I'm thinking, oh, I just realized. Okay, so I'm sorry. I'm going to pause and come back up here. And yes, so they do. It does have to be. We will go swimming only if it's sunny. It has to go in the form of R implies P. R happens implies that it's sunny. So we go swimming. That's implying that it's sunny outside. Okay, sorry. It does have to be that way. So do switch it because we are going to have to use that. And the reason we're going to have to use that is I'm noticing on these premises, two of them start with R and one of them starts with S, but none of them start with Q. You see that? Q is only in the very first one, which makes me think that I need to not conclude Q. I don't think that's going to help me. I think I want to conclude not P. I mean, I could, but I don't think it's going to actually help me. So I could do both, just like I did in the last problem. I can include both of them, but I don't think Q is really going to help me. Not P is partially going to help me. And the reason is P is also used in the second premise. So here, let me state the second premise. R implies P. That's another premise. So because I have not P, that's modus modus tollens. So modus tollens says I can conclude not R because P doesn't happen. So that's using modus tollens on 2 and 3, using those two to conclude not R. Okay. Then if not R happens, our third premise comes in. Not R implies S. So that's another premise. So if not R happens and not R implies S, then S is going to happen. So that's using modus ponens on numbers 4 and 5. Okay, now we're almost there because my last premise includes S. S implies T. That's another premise. So now we can conclude that T is going to happen, again, by modus ponens, using numbers 6 and 7. All right, so we were able to conclude T. I apologize for the confusion up there. I felt like it was subjective in the wording, but now I'm understanding. They wanted you to read it as, we are going swimming, which is implying that it's sunny outside. Okay, so I just wanted to make sure that that was correct before we moved on. Okay, so we do have some more rules for quantified statements. There's not as many, so don't panic, all right? But the rules we have, the rules that we just looked at, I went ahead and bullet pointed them for you. There's 8 of them: modus ponens, modus tollens, hypothetical syllogism, disjunctive syllogism, addition, simplification, conjunction, and resolution. There is a really nice table in the book, like a reference table on page 76, that has it all summed up really nicely, smaller than what the notes are. But you're welcome, of course, to use the notes. If you aren't aware, you are welcome to use the notes on the quizzes. All right, there's nothing wrong with that. Okay, so the first rule for for quantified statements. So now we're moving into the propositional language with the for all and there exists language, okay, is what's called the universal instantiation. Instantiation. Okay, wow, that's a stumbly thing. Here's how it says. Here's the form. We're given that for all x, p of x. Every x, proposition P is going to happen. So we can conclude then that it can happen for a very specific value C. Okay. So an example is all dogs is our X and Fido is a dog. Okay. So if we're going to use this format, all dogs are cuddly. That's P. All right, that's our P, that's our proposition. So we're saying all dogs are cuddly. That's the for all x, P of x. So based on that, we can conclude that Fido is cuddly. Oops. Therefore, Fido is cuddly. So if all dogs are cuddly, then this specific dog, Fido, is cuddly. Great. That's the universal instantiation. I feel like I'm saying that wrong, but oh well. Universal generalization. Now, this is used a lot in mathematics. In fact, I didn't even know that this was the name of this. I just used it all the time in my graduate school. Here's the idea. If you have a proposition that you assume for what we'll call an arbitrary C. Arbitrary is the word that implies I'm not being specific. I'm picking some random C. Okay. If that happens, if we're able to show for some random C something happens, we can conclude it happens for every value. It's hard to write that with an example, so we're not going to write it with an example, but we will see this in the next section, okay? So we'll come back to universal generalization. You'll get to see it in action, in a proof. Okay, existential instantiation. This one is using the there exists format. So if there exists an X with P of X with some property or proposition, we can conclude, oops, that P of C is going to happen for some element. So again, we're starting with a generalization statement and saying it applies for something specific. So here's an example. There is someone who got an A in the course. All right, let's call that person A. They call them lowercase a. and say that lowercase a got an A in the course. There you go. I think it would make more sense to call them X instead of A. I feel like it's weird to call A and then say the word A in the context of a grade. That's weird. Okay, we'll call it X. I feel like that's better. Here we go. Existential generalization. So this is the generalization version of this. Again, it's that we show that the proposition occurs for some element. And I'm not being specific. It just happens for one of them. So we can conclude then that there exists some element that this happens for. I just realized I didn't write this under the form. Sorry, I don't know why I write it right there. That's weird. So Michelle got an A in the class, so we can conclude, therefore, someone got an A in the class. In the class. All right. So those are the 4 additional rules we'll use with the for all and there exists, but I'm going to save the examples for the next video.